Just a quick update on this Ipod Nano 6 stuff. I've now got prototype of something closer to the final version. This is going to end up looking something like this, sort of display with the electronics on the back. So this gave us a couple of constraints. One is obviously everything had to fit on the footprint of the display, single-sided assembly to keep it nice and thin, but also because it's going to be a fairly large panel area, it really had to be two-layer to keep the cost down. Right, for this we moved away from using the FPGA that we had on the prototype ones, and the main reason for using the FPGA on that was we had to get something working quickly, and the FPGA was the quickest and easiest way of accurately emulating the original iPod display timings, because at the time we didn't really have any idea how many liberties we could take with respect to simplify it. The basic concept is that it's going to have onboard content that's uploaded offline and then displayed on demand, but also it may have to do stuff like putting overlays and text and stuff on it. So we needed something that could handle sort of more complex behaviour than an FPGA. The other thing about the FPGA is that you're actually quite restricted in packages. We couldn't really, so because this needs to be two-layer, it pretty much has to be in a quad type package, not a BGA. And there really aren't many small FPGAs in sort of chip packages smaller than 100 pin. So that pretty much ruled it out. But yeah, we wanted a processor on there, so we had a decent amount of memory to play with. We could do fonts and various other control stuff. I spent quite a long time looking at possible processors for this. The requirements were that I wanted a fairly, reasonably powerful processor so I could do font rendering and so on fairly quickly. It would have been nice to have had enough memory to have a full display buffer in there, but I had a good look and I really couldn't find anything suitable. There are a couple of ARM processors that have got enough, but the ARMs that have got a lot of memory have a nasty habit of sort of slicing up into different sections, so it's very hard to use a continuous buffer. And they also tend to come in quite large pin count packages and cost quite a lot. So what ends up with this is one of the relatively recent PIC32 devices, one of the low cost ones, the 32MX series. One of the nice things about it is it's got 32k of RAM, but the package is only 28 QFN, so in terms of the amount of RAM in a given package size, this was actually one of the biggest parts, partly because a lot of the ARM processors don't go down as low as 28 pin, so the packages tend to be a bit bigger. It's also pretty cheap. It's under £2. It runs at sort of 50 odd megahertz. It's got an internal RC oscillator that's accurate enough to do serial comms. But one of the other big things, it's got a parallel master port, which means that you've got an 8-bit I/O port that you can send data out of. It also has got DMA, so I can actually be feeding data out of a buffer, out of this parallel port fairly quickly, and be doing other things at the same time, like for example reading data in from the flash. So it's got a fairly fast UART. Unfortunately they've made a bit of a mess of the way they've implemented it, so you can't actually get super high performance without using DMA, and because of various reasons I don't really want to use DMA for the UART. They put a FIFO in it, which is quite common for fast UARTs, but they basically missed a bit out. When you've got a FIFO receiving data, one issue is, well, what happens if you get data? The idea is that instead of generating an interrupt on every byte, you generate, let's say you've got an 8-byte FIFO, you generate an interrupt every 8 bytes. So you get that interrupt, and then you read all 8 bytes out of the FIFO. The problem is, what happens if, say, you only receive 6 bytes? Now, implementations, for example, the NXP ARMs have a timeout interrupt. So if it doesn't see any bytes for, I think it's something like 1.5 or 2 character times, it will generate that timeout interrupt so you can empty out the FIFO, whatever's in it. Now, this doesn't have that. In some applications it doesn't matter, but it can be a bit of a pain to deal with. It means that if you just get 1 or 2 odd bytes coming in, with a fairly big separation, you pretty much have to implement a timeout, sort of timer that periodically just checks that something's come in. The flip side is that on a big packet, you've got potentially some leftover bytes at the end that aren't, if the packet size isn't a multiple of the FIFO size. And you basically have to manually implement a timer. So on this, when it's received a byte, it sets a fairly short interrupt timer, so if that timer times out before it receives more bytes, it then sort of deals with the rest of it. But it's a bit of an annoying omission. As I say, it's got DMA, which is nice. It's got a decent amount of flash, 32k RAM, self-program obviously, so I can update the firmware on it. The display interface I've used, this is a Lattice 4000 series CPLD. Now CPLDs are really like a very small FPGA effectively. The architecture is a bit different, but you can think of it as a very small FPGA. They're very cheap. They've got generally onboard non-volatile memory, and all I'm using this for at the moment is effectively as a serializer for the DDR data to the LCD. So I send it a byte from the parallel master port, and this then just serializes it at high speed and sends it out to the display. There's also a few other minor functions. For example, because this parallel master port uses quite a lot of pins, I'm using this as a bit of an I/O expander, so there's a few things like the LCD reset and a few other odds and ends. There's a LED on here as well that I'm just basically using this as an I/O expander. But the primary function is to generate this serial data out for the LCD. The other thing I might use it for, I currently, although we've got the 32 megabyte serial flash again, at the moment this is just passing straight through this chip doing nothing. But one thing that may be worth looking at, because the SPI port on this thing will only run at 25 megahertz, I may look at implementing a fast SPI read on this so that I can read a byte from here and it generates a fast burst of clock cycles and maybe uses the wide bus modes of the SPI, so I can effectively almost treat this as if it's a parallel device and get the data out of it more quickly. Until I actually get it all up and running, I'm not really sure how worthwhile that's going to be. The other sort of fairly nice thing about this PIC is, like a lot of the other PICs, a lot of the peripheral pin functions are mappable to different pins. Now unfortunately it's not quite as flexible as some of the other devices where you can map almost any device to any pin. It is actually quite constrained. There's, apart from the parallel master port, most of the other pins are remappable. The problem is each pin is only mappable to a subset of up to 8 peripherals, so you do have to be a little bit careful when you're deciding pin allocations. But it's better than having them all fixed, but not quite as flexible as devices like the PIC24. The other things on this board, there's a RS485 transceiver. There's probably going to be about 2,000 of these things in the whole installation eventually, and they're going to be sitting on a large number of RS485 buses, with probably something like probably sort of 80 to 100 devices on each bus. The only time that any serious amount of bandwidth is going to be used is when it's programming the flash, and it'll be able to overlay. For example, there's quite a long erase and write time on this, but it'll be able to sort of send data to several devices in parallel, then wait for them all to do the erase write time. But when the thing's actually running, all it's going to be doing is really telling which frame to display, so the bandwidth is going to be fairly small. Although it will, to upload data to all of them is going to take sort of quite a few hours, just because of the number involved. The other things we've got on here, there's a voltage regulator. This is going to run on a 24 volt bus because the power's going, the whole thing's being powered by down the PCB, and these, the eventual ones of these are actually going to be pretty long. They're going to be like a couple of meters worth. So we've got the power going down the PCB at 24 volts. Then we're regulating that down to 3 volts with a little switching regulator, and we've got the backlight power booster there, and that's pretty much it. Obviously these prototypes, these have just been laid out flat to make them easy to debug. So the final version is going to be, the LCD is going to be on one side, sort of held on with a clip, and then the flex goes through the board and into a little connector. One thing I quite like about these Lattice CPLDs, the programming is by a JTAG, as is on a lot of these type devices, but Lattice actually give you some code for programming using a microcontroller, and they've also got a utility that will take the device file and actually turn it into effectively a C source code for all the data. I've not actually got that running yet, but basically it allows you to embed your CPLD code into your program code, so when you update the firmware can also reprogram the CPLD. One of the things that I've implemented in here is just a version readback, so this could just read back a constant value from the CPLD to find out what version it is, so when it powers up it can check, can it read anything at all. If not, then chances are it's a blank CPLD because it's just been manufactured, so it can program the code in, and if a firmware update needs different functionality, it can read that version back, determine if it's changed or not, and then reprogram it if required. The other nice thing about microchip devices in general is that you can buy them pre-programmed from the factory at very low cost. It's literally a few pennies extra. So in manufacturing, there's no, we're not going to use to do any device programming. We've manufactured the thing that will have at least a bootloader in it, so we can then connect them all together and just upload new firmware in bulk as part of the test process. So that's actually quite a nice feature, which although you can get third-party programming houses to do device programming, the microchip ones are just so cheap, it makes a big difference. Well, the waveforms I'm using at the moment are about a halfway house between the original iPod ones and a very simple sort of pure SPI thing. I wanted to sort of do things gradually just to make sure it works. Also, I haven't had a chance to optimise this any further because I've got to get this ready for demonstration next week. But what I found, it does, it seems to be quite happy only getting clock when when you're sending a data packet, so it doesn't seem to need any clocking outside of the data packet. So this is actually sending 16 lines of data. It does seem to need a certain amount of clock before you start sending the data. This is again sort of a bit halfway between. I originally had it so it was just sending an idle clock until we actually were sending real data, and then switches over to a sort of a clock that occurs on demand. It may well be that this just needs a few extra dummy clocks. I haven't really had a chance to play around with that too much. But where the actual sort of data itself, that's now pretty similar to an SPI type thing. You know, it's quite happy to have these arbitrary length gaps between the clocks. So what I'm doing each of these pulses, this is the actual write from the PIC parallel master port, and then the CPLD is just generating 4 clock cycles, which of course there are 8 DDR clock cycles, and outputting the data. But there may well be some scope for simplifying this, which one of the things I want to try and do if possible is reduce the CPLD so I can get it down to the 32 macrocell one. So there may be some scope for simplifying this, but at the moment it's working, so I just need to concentrate on getting the rest of the software done before looking at any more optimising this. In terms of update speed, the limiting factor is really how fast I can throw data out of the PIC. I'm using DMA on the parallel master port, and sort of the PIC's running at 48 megahertz. It can go up to 50, but 48 gives some nicer baud rate dividers, so just left it at that. The extra 2 meg isn't going to make a lot of difference. Unfortunately, the DMA, you don't get completely consistent timing. Sometimes you get slight jitter between the timings, but that doesn't really matter because the LCD is happy about different gaps. That doesn't really matter. But we've got about 3.4 megabytes a second, which I was sort of expecting to be able to get a little bit more than that, but I think it's a limitation of the DMA memory architecture on the device. If we had a bigger device that had a 16-bit master port, we could probably get double that, but it's not too bad. On that's a complete display image, so we're getting about 32 milliseconds, so we could do 30 frames a second on that, but that's about the limit, and I think that's fast enough that the display is going to be look fairly instantaneous. And so the update is fairly close to instant. You do see there's a slight diagonal ripple visible. I don't know how visible that's going to be on the camera. There are 1 or 2 other entry modes on the display that might be worth fiddling with, that might just change the visual effect of the ripple. I'm not sure, but this is certainly fast enough, and in terms of the overall cost of the solution, I think we'd struggle to do much better for a solution that, if all it was doing was displaying data straight from the flash, then we could probably get it faster by doing it all in hardware in the FPGA or CPLD, but because we actually want it to go through the processor, I think that's fairly reasonable. I haven't yet got a fast update of images. I'm just sending data straight from the PC at the moment. Haven't yet implemented the SPI flash stuff, but it is actually working and displaying pictures.